To find the inverse of a matrix, we need to find the adjoint of that matrix first. Let us see what is an adjoint of a matrix. The adjoint of a square matrix A is defined as the transpose of the matrix capital Aij, where capital Aij is the cofactor of the element Aij and is denoted by adjoint of A. Let us consider a 2 by 2 matrix. We will find the adjoint of A. We will write the cofactors of each element A11, A12, A21, A22, and we have to transpose this matrix. Cofactor of A11 element is A22 and cofactor of A12 element is minus A21, because these two positions will get negative signs. And then cofactor of A21 is minus A12 and cofactor of A22 is A11, and transpose of this matrix, which is A22 minus A21 minus A12 A11. And we can write the adjoint of a 2 by 2 matrix directly. We interchange the main diagonal elements and change the sign of the other elements. Now we will write the adjoint of this A matrix directly. First step is interchanging the main diagonal elements, and the second step is changing the sign of the other elements. No need to transpose this step. See, these two answers are same. We can use this method only to write the adjoint of a 2 by 2 matrix. We cannot use this method to write the adjoint of a 3 by 3 matrix. To find the adjoint of a 3 by 3 matrix, we have to write the cofactors and then transpose that matrix. Theorem 1. If A be any given square matrix of order n, then A into adjoint of A equal to adjoint of A into A equal to determinant of A into I, where I is the identity matrix of order n. A into adjoint of A. Let us take A as a 3 by 3 matrix, and adjoint of A is transpose of the cofactors. To multiply these two matrices, we multiply the first row with the first column. The first column elements are the cofactors of the first row elements. We get A11, A11 plus A12, A12 plus A13, A13. So we are multiplying the first row elements with their corresponding cofactors, which will give us the determinant value of A. First row, first column element is determinant of A. And then we will multiply the first row with the second column elements. These are the cofactors of the second row elements. A11, A21 plus A12 into A22 plus A13 into A23. We are multiplying the first row elements with the cofactors of the second row. The answer will be 0. Similarly, the other element is also 0. Here we get 0, determinant of A, 0, 0, 0, determinant of A. Sum of the product of elements of any row with their corresponding cofactors will give the determinant value. Whereas, if the elements of a row are multiplied with the cofactors of any other row, then their sum is 0. We can take determinant of A common. To take a common number out from a matrix, we have to take it out from all the elements. Therefore, this becomes determinant of A into I. Similarly, we can prove that adjoint of A into A is determinant of A into I. Let us learn the definitions of singular and non-singular matrices. A square matrix A is said to be singular if determinant value of A is 0, and it is known as non-singular if determinant of A is not equal to 0. For example, let us take a 2 by 2 matrix, and the determinant value of this matrix is 4 minus 4, 0. Therefore, A is a singular matrix. For a singular matrix, we cannot find the inverse. Now, second example, we will find the determinant value of A. It is 8 minus 15, which is minus 7, not equal to 0. In this example, A is a non-singular matrix. Only for a non-singular matrix we can find the inverse. Theorem 2. If A and B are non-singular matrices of the same order, then A into B and B into A are also non-singular matrices of the same order. Theorem 3. The determinant of the product of matrices is equal to product of their respective determinants, that is, determinant of A into B is equal to determinant of A into determinant of B, where A and B are square matrices of the same order. That is, the determinant value of product of two square matrices is same as product of their determinant values. This is an important result. These theorems can be proved easily with examples. Remark, determinant of adjoint of A is determinant of A whole raised to n minus 1, where n is the order of matrix A. Consider a 3 by 3 matrix A. We know that adjoint of A into A is determinant of A into I, which is determinant of A 0, 0, 0, determinant of A 0, 0, 0, determinant of A. If we find the determinant value of adjoint of A into A, this becomes determinant of adjoint of A into determinant of A by theorem 3, and this is equal to determinant of A 0, 0, 0, determinant of A 0, 0, 0, determinant of A. Now, from a determinant, we can take common factors only from each row or from each column. So, we will take out determinant of A from the first row. We will get 1, 0, 0. Now, we will take it out from the second row. We will get square here, and from the third row. So, it becomes cube. And determinant value of a unit matrix is 1. Therefore, the answer becomes determinant of A the whole cube. Therefore, we got determinant of adjoint of A into determinant of A is equal to determinant of A the whole cube. We can cancel determinant of A on both sides. Therefore, we get the result determinant of adjoint of A is determinant of A the whole square if A is a 3 by 3 matrix. Therefore, in general, determinant of adjoint of A is determinant of A whole raised to n minus 1, where n is the order of the matrix A. This is also an important result. Now, we will see the formula for inverse of a matrix. Remember, a square matrix A is invertible if and only if A is non-singular matrix. We know that A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. If A is non-singular, we know that determinant of A is not equal to 0. We will divide the whole equation by determinant of A. We get A into adjoint of A divided by determinant of A is equal to adjoint of A divided by determinant of A into A is equal to determinant of A will get cancelled. We get I. Now, we will take this matrix as B. A into B is equal to B into A is equal to I. And we know the definition of an invertible matrix. AB equal to BA equal to I means A and B are inverses of each other. Therefore, A inverse is B matrix. Therefore, A inverse is B matrix is adjoint of A divided by determinant of A. This is the formula to find the inverse of a matrix. We find the adjoint of the given matrix A and divide by the determinant value of A. Exercise 4.5. Find adjoint of each of the matrices in exercises 1 and 2. First question, we will take the given matrix as A, 1, 2, 3, 4. Adjoint of a 2 by 2 matrix is easy to write. Interchange the main diagonal elements and change the sign of the other elements. Therefore, adjoint of A is 4, 1, interchanging the main diagonal elements, and we have to change only the sign of the other elements. This is the adjoint. No need to transpose this. And this method is applicable only for a 2 by 2 matrix. We cannot use this for a 3 by 3 matrix. Second question. Let the given matrix be A. We will write the adjoint of A, which is the transpose of the cofactors. Cofactor of 1, 3 minus 0, which is 3. Cofactor of minus 1, 2 plus 10, 12. That position gets a negative sign, minus 12. Cofactor of 2, 0 plus 6, which is 6. Cofactor of 2, minus 1, minus 0. But that position gets a negative sign, we get plus 1. Cofactor of 3, 1 plus 4, 5. Cofactor of 5, 0 minus 2, which is minus 2, but that position gets a negative sign, which becomes plus 2. Cofactor of minus 2, minus 5, minus 6, minus 11. Cofactor of 0, 5 minus 4, 1. That position gets a negative sign, minus 1. Cofactor of 1, 3 plus 2, 5. We will write the transpose of this, which is the adjoint. Don't forget the transposing step. Question 3. Verify A into adjoint of A equal to adjoint of A into A equal to determinant of A into I in exercises 3 and 4. We will take that as matrix A, 2, 3, minus 4, minus 6. We will find the adjoint, interchange the main diagonal elements and change the sign of the other elements. So we can write the adjoint directly, interchanging the main diagonal elements and changing the sign of the other elements. We got the adjoint. If you use this method to write the adjoint of a 2 by 2 matrix, don't transpose it. Now we will find A times adjoint of A. A matrix is 2, 3, minus 4, minus 6. And adjoint of A is minus 6, minus 3, 4, 2. When you multiply 2 by 2 matrices, you may go wrong by subtracting the corresponding products. You have to add them in matrix multiplication. First row into first column, minus 12 plus 12. First row into second column, minus 6 plus 6. Second row into first column, 24 minus 24. and second row into second column 12 minus 12. It is a 0 matrix. Now we will find adjoint of A into A. We will write adjoint of A first. Minus 6 minus 3 4 2 times A matrix 2 3 minus 4 minus 6. Let us multiply. First row into first column minus 12 plus 12. First row into second column minus 18 plus 18. Second row into first column 8 minus 8. Second row into second column 12 minus 12. This is also a 0 matrix. Now we will find determinant of A into I. Determinant value of A is minus 12 minus of minus plus 12, which is 0, into I matrix is 1 0 0 1. We will multiply this matrix by a scalar 0, so it becomes a 0 matrix. All three are same. Therefore, A times adjoint of A equal to adjoint of A into A is equal to determinant of A into I. Question 4. Let us take the given matrix as A. We have to find the adjoint of A. We will write the cofactors and transpose this matrix. To write the cofactors, we have to change the sign of these four positions. Cofactor of element 1. Cross multiply the remaining elements. 0 minus 0, 0. Cofactor of minus 1. 9 plus 2, which is 11. This position gets a negative sign, so minus 11. Then cofactor of 2. 0 minus 0, 0. Cofactor of 3. Minus 3 minus 0, which is minus 3. But this position gets a negative sign, which makes it plus 3. Cofactor of 0. 3 minus 2, 1. Cofactor of minus 2. 0 plus 1, which is 1. But this position gets a negative sign, which is minus 1. Cofactor of 1. 2 minus 0, 2. Cofactor of 0, minus 2 minus 6 minus 8. We have to change the sign, plus 8. Cofactor of 3. 0 minus of minus 3 plus 3. We will write the transpose of this matrix. Now we will find A times adjoint of A. First row into first column 0 plus 11 plus 0. First row into second column 3 minus 1 minus 2, 0. And then first row into third column 2 minus 8 plus 6, 0. Second row into first column 0 plus 0 plus 0. Second row into second column 9 plus 0 plus 2, 11. Second row into third column 6 plus 0 minus 6, which is 0. Third row into first column 0 plus 0 plus 0. Third row into second column 3 plus 0 minus 3, which is 0. Third row into third column 2 plus 0 plus 9, 11. And this is 11 times I. Now we will calculate adjoint of A times A. Adjoint of A should be written first. This product is also 11, 0, 0, 0, 11, 0, 0, 0, 11, which is 11 times I. Now determinant value of A is, we will expand along the first row, which is 11. Therefore, A into adjoint of A is equal to adjoint of A into A is equal to determinant of A into I. Next question. Find the inverse of each of the matrices if it exists given in exercises 5 to 11. Question number 5, we will take it as matrix A, 2, minus 2, 4, 3. We will first find the determinant value of A, which is 6 plus 8, 14, not equal to 0. Therefore, A inverse exists. Now we will find adjoint of A. For a 2 by 2 matrix, it is easy to write. We will interchange the main diagonal elements and change the sign of the other elements. We will get the adjoint 3, 2 and change only the sign for the other elements. This is the adjoint. A inverse is equal to 1 by determinant of A into adjoint of A. Determinant value is 1 by 14 and adjoint is 3, 2, minus 4, 2, which is equal to 3 over 14, 1 over 7, minus 2 over 7 and 1 over 7. Or we may leave the answer in this form. Question 6, we will take it as A matrix, minus 1, 5, minus 3, 2. We will first calculate the determinant value of A, which is minus 2 plus 15, 13, not equal to 0. Therefore, A inverse exists. We will write adjoint of A, interchange the main diagonal elements and change the sign of the other elements. We get the adjoint. This method is applicable only for a 2 by 2 matrix. A inverse formula is 1 by determinant of A into adjoint of A, 1 by 13 times 2 minus 5, 3 minus 1. We may leave the answer in this form or we can write it as 2 over 13 minus 5 over 13, 3 over 13 minus 1 over 13. Question 7. Now this is a 3 by 3 matrix. We will first find the determinant value of A. We will expand along the first column, 1 into 10 minus 0, which is 10. Other two elements are zeros. So this is not equal to 0. Therefore, A inverse exists. We will write adjoint of A, which is the transpose of the cofactors. Cofactor of 1, 10 minus 0, which is 10. Cofactor of 2, 0 minus 0, 0. Cofactor of 3, 0 minus 0, 0. Cofactor of 0, 10 minus 0, 10. But this gets a negative sign, so minus 10. Cofactor of 2, 5 minus 0, 5. Cofactor of 4, 0 minus 0, 0. Cofactor of 0, 8 minus 6, 2. Cofactor of the next element 0, 4 minus 0, which is 4. That position gets a negative sign, which makes it minus 4. Cofactor of 5 is 2 minus 0, 2. The transpose is 10, 0, 0, minus 10, 5, 0, 2 minus 4, 2. A inverse is 1 by determinant of A times adjoint of A, 1 by 10 times 10 minus 10, 2, 0, 5 minus 4, 0, 0, 2. You may leave the answer in this form, or we may multiply by 1 by 10 and write it as 1 minus 1, 1 by 5, 0, 1 by 2 minus 2 by 5, 0, 0, 1 by 5. Question number 8. We will take the matrix as A. We will first find the determinant value of A. We will expand along the first row 1 into minus 3 minus 0, which is minus 3, not equal to 0. Therefore, A inverse exists. We will find the adjoint of A. Adjoint is transpose of the cofactors. Cofactor of 1 is minus 3 minus 0, which is minus 3. Cofactor of the next element 0 is minus 3 minus 0, minus 3. Here we have to change the sign, which becomes plus 3. Then cofactor of the next 0 is 6 minus 15, which is minus 9. Cofactor of 3 is 0 minus 0, 0. Cofactor of the next element 3 is minus 1 minus 0, which is minus 1. Then cofactor of 0 is 2 minus 0, 2. But that position gets a negative sign, which makes it minus 2. Then cofactor of 5 is 0 minus 0. Cofactor of 2 is also 0 minus 0. Cofactor of minus 1 is 3 minus 0, which is 3. We will write the transpose. A inverse formula is 1 by determinant of A into adjoint of A. We get 1 divided by minus 3 times minus 3, 0, 0, 3, minus 1, 0, minus 9, minus 2, 3. The answer is 1, 0, 0, minus 1, 1 divided by 3, 0, 3, 2 divided by 3 and minus 1. Question 9. We will take the given matrix as A. The determinant value of A matrix is, expanding along the first row, we get 2 times minus 1 minus 0, middle term gets a negative sign, 4 minus 0 plus 3 times 8 minus 7, minus 2 minus 4 plus 3, which is minus 3, not equal to 0. Therefore, A inverse exists. We will write the adjoint of A, which is the transpose of the cofactors. Don't forget the transposing step. Cofactor of 2, minus 1 minus 0. Cofactor of 1, 4 minus 0, 4. But that position gets a minus sign, so minus 4. Cofactor of 3, 8 minus 7, 1. Cofactor of 4, 1 minus 6, minus 5. But minus of minus 5 will become plus 5. Cofactor of minus 1, 2 plus 21, 23. Cofactor of 0, 4 plus 7, 11. Minus 11 it becomes. Cofactor of minus 7, 0 plus 3, 3. cofactor of 2. 0 minus 12 minus 12, but it becomes plus 12. Cofactor of 1 is minus 2 minus 4 minus 6. We will write the transpose of this. A inverse formula is 1 by determinant of A into adjoint of A. 1 divided by minus 3 times the adjoint. This is the answer. Question 10. We will take the given matrix as A. Let us find the determinant value of this matrix. We will expand along the first column. 1 into 8 minus 6. The middle term is 0 plus 3 times 3 minus 4. 2 minus 3, which is minus 1, not equal to 0. Therefore, A inverse exists. If it is a singular matrix, inverse does not exist. Let us find the adjoint of matrix A, which is the transpose of the cofactors. Cofactor of 1 is 8 minus 6, 2. Cofactor of minus 1 is 0 plus 9, 9. That gets a negative sign, minus 9. Cofactor of 2 is 0 minus 6, minus 6. Cofactor of 0 is minus 4 plus 4, 0. Cofactor of 2 is 4 minus 6, minus 2. Cofactor of minus 3 is minus 2 plus 3, which is 1, but that position gets a negative sign, minus 1. And then cofactor of 3 is 3 minus 4 minus 1. Cofactor of minus 2 is minus 3 minus 0. That position gets a negative sign, plus 3. Cofactor of 4 is 2 minus 0, 2. Let us write the transpose. A inverse formula is 1 by determinant of A into adjoint of A. The answer is 1 divided by minus 1 times the adjoint. The answer is, we have to change the sign throughout. Question number 11. The given matrix is 1 0 0, 0 cos alpha sin alpha, 0 sin alpha minus cos alpha. Let us find the determinant value of A. Expanding along the first row, we get minus cos square alpha minus sin square alpha. Minus sign is common. Cos square alpha plus sin square alpha is 1. Therefore, the determinant value is minus 1, which is not equal to 0. Therefore, A inverse exists. Now, we will find the adjoint of matrix A, which is the transpose of the cofactors. Don't forget the transposing step. Cofactor of 1 is minus cos square alpha minus sin square alpha, which is minus 1. Cofactor of the next element 0 is 0 minus 0. Cofactor of the next element is also 0. Cofactor of this element is 0. Cofactor of A22 element is minus cos alpha, and cofactor of A23 element is sin alpha minus 0. that position gets a negative sign, so minus sin alpha. Cofactor of A31 element is 0. Cofactor of A32 element is sin alpha minus 0, but negative sign is there, minus sin alpha. Cofactor of A33 is cos alpha minus 0, which is cos alpha. We will transpose this, which is the same because it is a symmetric matrix. A inverse formula is 1 by determinant of A into adjoint of A. Determinant value is minus 1. We have to change the sign throughout. And this is the answer. Question 12. A is equal to 3725 and B is equal to 6879. Verify that AB the whole inverse is equal to B inverse times A inverse. Reversal law for inverse. We have reversal law for transpose also, but here we have to prove for inverse. We will first find A times B. First row into first column, 18 plus 49. First row into second column, 24 plus 63. Second row into first column, 12 plus 35. Second row into second column, 16 plus 45. This is 67, 87, 47 and 61. We will find determinant value of A into B. We know the result that determinant of AB is determinant of A into determinant of B. Determinant of A is 15 minus 14 and determinant of B is 54 minus 56. 1 into minus 2, which is minus 2. This is not 0, so we can find inverse of AB. AB the whole inverse is 1 by determinant of AB into adjoint of AB. 1 by minus 2 times. We interchange the main diagonal elements and change the sign of the other elements. Minus 87 minus 47. Now we will find the right hand side. B inverse times A inverse, which is 1 by determinant of B into adjoint of B into 1 by determinant of A into adjoint of A. Determinant of B is minus 2 and determinant of A is 1. We will write the adjoint of B, interchanging the main diagonal elements and changing the sign of the other elements. Now adjoint of A, interchanging the main diagonal elements and changing the sign of the other elements. Minus half into 45 plus 16. Here you have to add the corresponding products. By mistake, don't subtract. First row into second column, minus 63 minus 24. Second row into first column, minus 35 minus 12. Second row into second column, 49 plus 18. We get minus half into 61 minus 87 minus 47 and 67. And LHS and RHS are equal. Therefore, AB the whole inverse is B inverse into A inverse. This is an important property of inverses. Question 13. If A is 3, 1, minus 1, 2, show that A square minus 5A plus 7I is equal to 0 matrix. Hence find A inverse. We will first calculate A square. A square is A times A. First row into first column. 9 minus 1. First row into second column. Second row into first column. Second row into second column. We get 8, 5, minus 5 and 3. We will calculate this expression. A square minus 5A plus 7I. A square is 8, 5, minus 5, 3. Minus 5 times A. We will multiply each and every element by 5. 15, 5, minus 5, 10. Plus 7 times I is 7007. 8 minus 15 plus 7 is 0. 5 minus 5, 0. Minus 5 plus 5 is 0. And 3 minus 10 plus 7 is also 0. We get the 0 matrix O. Now second part of the question is, hence find A inverse. Hence find A inverse means using the previous result we have to find A inverse, not by adjoint method. Now determinant of A is 6 minus of minus 1 plus 1, 7, which is not 0. A inverse exists. Now the equation which we have proved is A square minus 5A plus 7I is equal to 0. We will pre-multiply this equation by A inverse. We have to either pre-multiply or post-multiply by A inverse, as matrix multiplication is not commutative. We get A inverse into A square, which is A into A, minus 5 times A inverse A plus 7 times A inverse I is equal to A inverse into 0 matrix. We know that A inverse into A is I, and A inverse into I is A inverse. Therefore, this becomes I into A, which is A, minus 5 times I plus 7 times A inverse is equal to 0 matrix. From which we can find A inverse. 7 times A inverse is 5I minus A. 5I is 5005. And A matrix is 3, 1, minus 1, 2. Therefore, A inverse will be 1 by 7 times 5 minus 3, 0 minus 1, 0 plus 1, 5 minus 2. By using adjoint of A, you will get the same answer, but it is wrong. The question says, hence find A inverse. So, using the previous result, we have to find A inverse. Question 14. For the matrix A, 3, 2, 1, 1, find the numbers A and B such that A square plus A plus BI is a 0 matrix. We will find A square, which is A times A. Nine plus 2, 11. 6 plus 2, 8, 3 plus 1, 4, 2 plus 1, 3. The given expression A square plus A plus BI is equal to A square is 11, 8, 4, 3. A times A. We will multiply the matrix by the scalar A. 3A, 2A, A. Plus BI. B0, 0B, and this is given as a 0 matrix. We will add these three matrices. 11 plus 3A plus B, 8 plus 2A, 4 plus A, 3 plus A plus B. this is equal to a 0 matrix. If two matrices are equal, the corresponding elements must be equal. We will equate these two. We get 4 plus A equal to 0. A value is minus 4. By equating these two elements also, we get A equals minus 4. Now let us equate these two elements. 3 plus A plus B is 0. B is equal to minus 3 minus A, which is minus 3 plus 4. B value is 1. By equating these two elements also, we get the same answer for B. Question 15. For the matrix A, show that A cube minus 6A square plus 5A plus 11I equal to 0. Hence, find A inverse. We will find A square. First row into first column. First row into second column. First row into third column. Then second row into first column. Second row into second column. Second row into third column. Third row into first column. Third row into second column. Third row into third column. We get 4, 2, 1, minus 3, 8, minus 14, 7, minus 3, 14. Now we will find A cube. A cube is A square times A, or A times A square also we can write. Into A matrix. First row into first column. First row into second column. First row into third column. Second row into first column. Second row into second column. Second row into third column. Third row into first column. Third row into second column. Third row into third column. The answer is 8, 7, 1, minus 23, 27, minus 69, 32, minus 13 and 58. Now the given expression A cube minus 6A square plus 5A plus 11I is equal to A cube is 8, 7, 1, minus 23, 27, minus 69, 32, minus 13, 58, minus 6 times A square. We will multiply A square matrix by 6. 24, 12, 6, minus 18, 48, minus 84, 42, minus 18, 84, plus 5 times A. A matrix should be multiplied by 5. 5, 5, 5, 5, 10, minus 15, 10, minus 5, 15, plus 11i, 11, 0, 0, 0, 11, 0, 0, 0, 11. We will subtract the first two matrices. 8 minus 24 is minus 16. 7 minus 12, minus 5, minus 5, minus 5, minus 21, plus 15, minus 10, 5, minus 26. We will add the last two matrices. Adding these two matrices, we get a zero matrix. Now the second part of the question is, hence find A inverse. We will find the determinant value of A, expanding along the first row. 1 into 6 minus 3, minus 1 into 3 plus 6, plus 1 into minus 1 minus 4. 3 minus 9 minus 5. Minus 11, which is not 0, therefore A inverse exists. Now the equation which has been proved is A cube minus 6A square plus 5A plus 11I is a zero matrix. We will pre-multiply by A inverse. We get A inverse A times A square. A cube has been written as A into A square minus 6 times A inverse AA plus 5 times A inverse A plus 11 times A inverse I equal to A inverse into 0 matrix. Matrix multiplication is not commutative. So either we have to pre-multiply this equation by A inverse or post-multiply by A inverse. A inverse into A is I, and A inverse into I is A inverse. I into A square is A square. I into A is A. A inverse into A is I. 11 times A inverse equal to 0, from which 11 times A inverse is 6A minus A square minus 5I equal to 6 times A matrix is 6, 6, 6, 6, 12 minus 18, 12 minus 6 and 18 minus A square matrix is 4, 2, 1 minus 3, 8 minus 14, 7 minus 3, 14 minus 5I is 5, 0, 0, 0, 5, 0, 0, 0, 5, which is equal to minus 3, 4, 5, 9, minus 1, minus 4, 5, minus 3, minus 1. Therefore, A inverse is 1 by 11 times this matrix. Question 16. A matrix is 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. We have to prove that A cube minus 6A square plus 9A minus 4I is equal to a 0 matrix, and hence find A inverse. We will first find A square, which is A into A. Four plus 1, which is 6, minus 2 minus 2 minus 1, minus 5, 1 plus 1 plus 2, 5, minus 2 minus 2 minus 1, minus 5, 1 plus 4 plus 1 is 6, minus 1 minus 2 minus 2 is minus 5, 2 plus 1 plus 2 is 5, minus 1 minus 2 minus 2, minus 5, 1 plus 1 plus 4, 6. A cube is A square times A or A times A square. Both will give you the same answer. Times A matrix. Twelve plus 5 plus 5, 22. Minus 6 minus 10 minus 5, minus 21. 6 plus 5 plus 10, 21. Minus 10 minus 6 minus 5, which is minus 21. 5 plus 12 plus 5, 22. Minus 5 minus 6 minus 10, minus 21. 10 plus 5 plus 6, 21. Minus 5 minus 10 minus 6, minus 21. 5 plus 5 plus 12 is 22. We will calculate the expression A cube minus 6A square plus 9A minus 4I. A cube. Minus 6 times A square, which is 36, minus 30, 30, minus 30, 36, minus 30, 30, minus 30 and 36, plus 9 times A, 18, minus 9, 9, minus 9, 18, minus 9, 9 minus 9, 18, minus 4 times I, 4 0 0 0 4 0 0 0 4. We will subtract the first two matrices. We get minus 14, 9 minus 9, 9 minus 14 plus 9, minus 9 plus 9 and minus 14. And let us subtract the last two matrices. We get 14 minus 9, 9, minus 9, 14 minus 9, 9 minus 9, 14. We get 0, 0, 0. Which is a 0 matrix. Now determinant value of A is, we will expand along the first row, 2 times 4 minus 1, minus of minus plus 1 into minus 2 plus 1, plus 1 into 1 minus 2, which is 6 minus 1 minus 1, 4, not equal to 0. Therefore, A inverse exists. The equation which we proved is A cube minus 6A square plus 9A minus 4I is 0. We will pre-multiply by A inverse. Or we can do post multiplication also. A inverse A square minus 6 A inverse AA plus 9 A inverse A minus 4 A inverse I is equal to A inverse into 0 matrix. A inverse into A is I into A square is A square, minus 6 times A inverse into A is I into A is A, plus 9I minus 4A inverse is a 0 matrix. Therefore, 4 times A inverse is A square minus 6A plus 9I. 4 times A inverse is equal to A square minus 6 times A plus 9 times I. 6 minus 12 plus 9, 3. Minus 5 plus 6 plus 0, 1. 5 minus 6 plus 0, minus 1. Minus 5 plus 6 is 1. 6 minus 12 plus 9 is 3. Minus 5 plus 6, 1. 5 minus 6, minus 1. Minus 5 plus 6 plus 1. 6 minus 12 plus 9 is 3. Therefore, A inverse is 1 by 4 times 3, 1 minus 1, 1, 3, 1, minus 1, 1, 3. Question number 17. Let A be a non-singular square matrix of order 3 by 3. Then, determinant of adjoint of A is equal to. We know the formula for determinant of adjoint of A, which is determinant of A whole power n minus 1, where n is the order of the matrix A. Here n is 3. Therefore, determinant of adjoint of A is determinant of A whole raised to 3 minus 1, 2. Option B is correct. 17th and 18th are important questions. If A is an invertible matrix of order 2, then determinant of A inverse is equal to. We have to find the value of determinant of A inverse. We will use the equation A into A inverse is equal to I. We will take determinant on both sides. And we know that determinant of AB is determinant of A times determinant of B. Using this result, the left hand side becomes determinant of A times determinant of A inverse. We know that determinant value of the identity matrix is 1. Therefore, determinant of A inverse is 1 by determinant of A. Option B is correct.